So reaction mechanism 6 picks up essentially where we left off with reaction mechanism 4 with a hemiacetal. So let's go ahead and draw our hemiacetal. And what we're going to have here is essentially a nucleophilic addition-elimination reaction. So with our hemiacetal, we actually do have a good leaving group right now. Actually, this is going to be a hemiketal here, so this is the reaction mechanism number 4 product. Now we can make this be a better leaving group by protonating it. So that's going to be a general theme that we're going to see throughout many of our mechanisms, is that if we want a leaving group to leave, we often can protonate it to make it a better leaving group. So now we've got a good leaving group here, and importantly what we're going to see is this leaving group leaves because the lone pair on the oxygen atom forces it out. We don't have carbocation formation here. So this lone pair of electrons is going to generate a pi bond, and that is going to allow for the breakage of the weakest sigma bond, which is going to be to our best leaving group, which in this case is the protonated water. So to just kind of highlight here, we're going to have water leaves because it is forced out. We do not want to see carbocations here. We would not want to see this guy just kind of departing on its own. We would want to make sure that we didn't leave a carbocation intermediate. So continuing with this mechanism now, what we end up with is a carbonyl containing compound that is very electrophilic. And in being very electrophilic, now is where we're going to see our incoming nucleophile in our second equivalent of alcohol. So nucleophilic attack now by our alcohol, which remember alcohols are not very strong nucleophiles, so we're not going to have something here that's going to be very strong as an as a nucleophile. So if we make our electrophile more electrophilic, that helps with that chemistry. We end up now with an intermediate here in our protonated ketal, and we're going to see water here is going to facilitate the deprotonation of this guy, returning these electrons back to oxygen and leaving us with our ketal product. So again, looking at the difference in the structure between a hemiketal and then a ketal. A ketal essentially has 2 ether connections off of a single carbon atom, whereas the hemiacetal has 1 ether connection and then an alcohol functional group. And again, that alcohol functional group has the ability to be protonated, made into a good leaving group, depart with the assistance of our internal nucleophile, generate a very electrophilic carbonyl-like intermediate here, which now will react with our alcohol to generate our ketal. So kind of some comments here. Again, this mechanism really picks up where 4 left off. Reaction mechanism 7 is going to be very simple for you if you kind of recognize the pattern that this is taking. But again, a nucleophilic addition reaction like we have with ketones and aldehydes, again, the nucleophile here, again, being a molecule with a lone pair of electrons on the attacking atom. We're going to see that generally with alcohols and amines. When we do have that nucleophile as an alcohol or amine, we can have chemistry continue here. We're going to see this nucleophilic addition elimination reaction by eliminating water. So remember what we had here. We had in this case a ketone that when we had our nucleophilic attack on the carbonyl carbon, we generated a tetrahedral intermediate whose only option was to protonate here. Well, because we have an incoming nucleophile that has a lone pair of electrons here, we can protonate this alcohol make it into a good leaving group, and have those electrons help push that out. So again, having that nitrogen or that oxygen atom here is really what's key. Having alcohols and amines as our nucleophiles. So two common mistakes I kind of want to highlight here, and I'm going to draw these as mechanisms. So the first one here is a common mistake that students make is they want to attempt the addition of the alcohol via an SN2-like mechanism. Generally, this is not going to occur. It's too sterically hindered. Or again, they're going to try to have the protonated water depart, leaving a carbocation. Remember, we don't tend to see carbocations in our biochemical reaction mechanisms. Even if it was formed, we'd immediately have stabilization by that adjacent electron pair on the oxygen atom, or that lone pair on the adjacent oxygen atom. So I'm going to draw what these would look like. And again, these are common things that students will do, but I want to make sure to highlight here that these are not correct mechanisms. So everything below here is not correct, but common student mistakes. Some people want to do this SN2-like chemistry, where we'd have, again, our hemiacetal here. Even if you had gone ahead and protonated it and made it into a good leaving group, and we had our alcohol here, people want to do this. This guy comes in, that departs, and we get to our product. And it looks like a nice mechanism, right? It looks like it would be plausible. Just finishing this out here so we can kind of discuss this. We do get to something that looks very similar to what we have here. But again, this mechanism does not occur via this SN2-like attack. It's too sterically hindered, so we're not going to see that. The other mechanism I'll kind of comment on that I frequently see is we're going to see carbocation formation. So again, starting with our same protonated hemiketal here. So again, protonated hemiketal here. Oftentimes people want to take the first step here and just have this good leaving group leave, and then we'll be left with this carbocation intermediate. It's so hard for me to even draw these because, again, I know that they are not what we see here. I'm going to make that look a little bit more like a carbocation there. So we do not see carbocations in our reaction mechanisms here. And just to highlight, even if this guy did happen to form, the fact that there is an adjacent lone pair of atoms on this oxygen that could come down and help fix this incomplete octet. Remember, incomplete octets with any atom, when you're drawing kind of the best Lewis structure, best resonance form is going to be one of the least contributing forms, because having an incomplete octet is one of the most unstable things you could have. And so that's not going to happen here because those electrons could easily be pushed down. So again, just kind of some comments on the biochemical application of this, right? Ketal formation is found in biochemistry when cyclized sugars polymerize. So remember, when we formed those cyclic sugars, that was the formation of the hemis, where we had a hemiketal or a hemiacetal, depending on whether we started from an aldehyde-containing sugar or a ketone-containing sugar. So when we polymerize those, that's going to be through the creation of a glycosidic bond. And so we'll see this chemistry played out when we learn about carbohydrate structure in a few chapters. But again, sugars who have that carbonyl that we've kind of locked up in this ketal or polymerized forms, we refer to these as non-reducing, since they are more than one step away from having that reactive carbonyl functional group that can undergo redox chemistry. So again, the purpose of doing these reaction mechanisms, what we're going to see with reaction mechanisms 4 through 7, is the first thing we do is we cyclize our sugars, and that's the first step in protecting that carbonyl. And then the second step in polymerizing allows us to further functionalize our sugars by polymerizing them, but that also really locks up that carbonyl in not being reactive. And so we say that that would be a non-reducing portion of a carbohydrate.